welcome you and all of you to the Chemical Engineering Teaching Labs 3. So I'm gonna get this, I will explain you in a minute. Please come in. So all that you can see here, all this room, is the Chemical Engineering Teaching Labs 3, where our students in third year come here to do hands-on and practical experimentation in the lab. Our laboratory is actually the only one that has received the Bronze Award of the University in Sustainability, the only teaching lab. Now we have actually upgraded into Silver Award, so we have made it even more sustainable than it was before. So here in this lab we have a wide range of experiments very much related with chemical engineering applications and chemical engineering processes. So in first year, second year, the students normally they see the principles, they study the theory, but it's only until third year when they have the opportunity and the chance to play and to understand all these principles and theory from a practical point of view. So I'm gonna give you a small tour. I'm gonna show you what are the type of experiments that we do here. So here, for example, this is a phase change boiling experiment where the aims of this experiment is basically to study the boiling behavior of a fluid at different heating conditions. So in this experiment specifically we have a volatile liquid which boiling temperature is lower than 60 degrees, and we have a heater to supply heat to the working fluid. The heater is here. We don't have fluid here. We are substituting the fluid we are kind of revamping the experiment. And what we do here, we apply different heating power. We get different temperatures of the heater and of the liquid, and we are inducing different behaviors from natural convection for low temperatures. We start with some nucleation of bubbles when the temperature is that of the boiling temperature. When we heat up much farther, we create a film of vapor around the heater, and the kind of the heat transfer and the cooling is ineffective. This is very important for applications such as microchip cooling or also for nuclear reactors cooling. We move into this other experiment here, also heat transfer experiment. This is a single tube condenser heat transfer and also involves phase change. This vessel here allows to change the different working fluid. Here we are studying acetone, ethanol, and water. They have different boiling points, and they have also different condensation heat transfer performance, all to the different latent heat. So here again we have steam, we have a boiling fluid here, and we pass a cooling fluid through this U-pipe tube, and based on the different already proposed correlations for single phase, we are able to calculate what is the heat transfer coefficient of phase change during condensation depending on the working fluid. Here another experiment related to phase change is the dryer experiment. Dryers are almost used in almost any kind of process. Is one of the first steps when we have the raw material that arrives before the process. We need to dry, we need to remove the moisture content. It can be also applied and utilized for study some crystallization, maybe crystallization processes. And here we have a compressor, brings all the air inside. we can control the temperature of the air before arriving into the sample with this heater. There is a cartridge heater here inside. Hot air from the ambient passes through the middle section where we are placing our solid to dry in a petri dish. We typically use sand, that should be somewhere here. And then we have a balance and we are able to monitor what is the weight mass loss in time. We have also different controllers here. So with this we can estimate the velocity of the air. All these parameters necessary for us to be able to calculate the different heat transfer performance and, more importantly, the drying performance of the equipment that is essential to be able to design these processes at the industrial level. We move a little bit into another drying setup. The Buki spray dryer. This is very much used in pharmaceutical industries, for example. Here we will have a solution. Typically, we are using some calcium carbonate or some sodium hydroxide that is dissolved in the solution at concentrations below the critical concentration, and we will pass the solution through an atomizer that it will make very small drops, and as the drops go down through this vessel here, and because there is also hot air coming down, the particles will dry and we will be able to obtain particles with different sizes depending on the parameters that we study. Typically here we study the velocity of the atomizers, of the particles, and what is the different temperatures of the drying. And based on those parameters, using this cyclone here, we are able to capture the particles that we later on check on our stereoscope what is the different sizes or the different crystallization of the particles. Another heat transfer experiment in this case without any phase change, is the double pipe heat exchanger here. As you can see here, we are also filming this experiment to try to account for this hybrid delivery. We want to run all these experiments online, as we cannot do it now within the lab face to face. So here it also resembles the kind of exchangers that we have in industry. Also very important to be able to utilize some heating duties or heating hot streams that otherwise will be wasted or just released into the ambient. So here you can see we have 5 different heat exchangers. We have, as you can see, 2 different rotameters. One is for the hot fluid, another one is for the cold fluid. And we have this special valve here also that allows us to run the fluid either in co-current or in counter current with the different heat transfer behavior. And I can give you an example of, so the outer shell is typically the same. What we're investigating here is the properties of the inner shell. We are having hot fluid in the inside, cold fluid outside, and this will be our heat exchanger 5. Is copper, different thermal conductivity material, stainless steel. Another important variation that we have in the outer shell of this heat exchanger 3 is these baffles that you can see here, these kind of cross sections. This what is making is the fluid in the outer shell to kind of divert and move and create a little bit of mixing and turbulence that typically gives more heat transfer. And there is also another of the tubes where there is a mesh inside. Again, this kind of creates turbulences and provides greater heat transfer. And here, just quickly, we have here two experiments that they are just replicated. They are the same. This is the thermoelectric heat pump experiment. So in this experiment, as you can see here, we have a cell, and we have also different rotameters to control the hot water and the cold water passing through the cell. As two different currents of cold water, hot water passes through this cell, they are actually able to create some small current. And the same, we can also apply current. This is the cell that we have. We can also apply some voltage to the cell to give also heat or remove heat from this device. And the students are able to play a little bit with the different variables, the different flows, and to record all the temperatures and the performance of this thermoelectric heat pump. Here, so I finished with all the heat transfer experiments. Also, we have a range of packed bed experiments or columns, typically used in absorption for CO2 capture, or when we want to maximize the surface area of contact between a gas and a liquid. So that was the example of carbon capture, where you have CO2 in the flue gas, for example, and you pass it through a liquid flow that contains some CaCO3 that will actually absorb the CO2. So how it is designed, this experiment is only, for now, is only to study and understand what is the hydrodynamic performance of this packed bed. As you can see here, we have two in series. Inside the packed bed, we have these, they are called rising rings. These are made of glass in this case. And as you can see, they are randomly oriented. And what we do in this experiment, we have a compressor that helps us to pump the air from bottom to top, while we have a tank and a different pump that it will bring the water from the bottom. The water will distribute along the surface of these random packed resin rings, and the air will go from the bottom and it will increase the contact. And what we want to see here is what are the different pressure drops, what is the working performance of this experiment. You may realize that if we are pouring lots of water from the top and also the gas flow from the bottom is very high, at some point the gas, it will start to push the water in the upwards direction, and we will get the flooding of the column that is very undesirable in industry, as the packed bed will lose performance and it will not work. Very similar one, kind of a continuation of that experiment, is these three other columns, also for absorption. As you can see here, this packing is very similar to the glass one shown before, a little bit thicker, and the material is also different. Material is very important because sometimes this is a kind of ceramic, so this material is very good to resist very high temperatures or to resist maybe flue gases that are coming from combustion, for example. And the interesting thing of these three columns is that, as you see here, this is randomly oriented packing, whereas these other two are actually quite oriented in a nice packing fashion. So with these two columns, we are able to see what is the different void fraction inside and what is the different hydrodynamic performance because of the packing inside. That in the end is what gives the different flooding conditions or the different ranges of air and water that we can deal with. Yeah, let's see another one of the typically packed beds. Here, this is called the fluidized or collapsing bed. Here in these columns, very similar to the ones that you saw before. Again, we have also some manometers, some rotameters. We introduce the air from the bottom to the top. And in this case, what we are gonna have in the middle is gonna be solid particles that are in very small size. So here is an example of the particles you can see there. As you can see here, is a very fine, very small powder. And these particles are typically, sometimes they are like catalyzers, and you pass some flow of air from the bottom, the air or the flow that we want to treat, and they will react with the particles very efficiently because the gas and the particles distribution and the surface area is very high. And we are building here, is still under construction, a very similar setup as the fluidized collapsing bed. But here, as you can see, we want to also study what is the effect of the different diameters of the pipe. And more importantly, the effect also of the distributor at the bottom. This is very important to create a kind of homogeneous flow of air. Besides these kind of packed bed experiments, we do also have some separation experiments related to separation processes. This is one of them. This is filtration 1. And in this experiment, we will prepare a solution of calcium carbonate in kind of high concentrations, and we will pass the solution through these filtration membranes that you see here. And because the flow will be from left to right, we will start to obtain the filtrate all this here, creating a cake. And what this experiment consists on is on passing different flows, different working pressures, and see what is the performance of the hydrodynamic performance of the equipment. Again, this is very important. We want to design in a good fashion what will be the surface area that we need for a given application, for the range of working pressures that we can work with. We have filtration 2 here, a little bit more pilot scale, bigger scale than the one you showed earlier. Here are our plates. So all the flow with the different calcium carbonate is gonna pass from right to left, and we are gonna put some. Will be our filter that it will be introduced within these plugs, and again we apply some pressure, we apply some flow, and we will start having the different thickness of the cake we will start growing in time. And because of the greatest thickness of the cake, of the thing that we are filtrating, also the working pressure of the system is going to be different, and the hydrodynamic performance is going to be completely different. Third experiment about filtration. This is our desalination membrane. So in this experiment, we are gonna make also a solution, in this case of very low concentrations, and we are gonna pass it through this membrane that it actually works in a kind of radially outwards flow. And in order to be able to measure what is the different concentrations, because we use here some type of salt. We will be using also a conductive meter and pH meter for this purpose. And I think we only have left experiments related to reaction that are in this area here. Just to point you out, we have this experiment here, it's being built. This is gonna be a distillation column. As all of you are aware, distillation is very important in Scotland, about all the distillation of whiskey. So I think it's very important for all of us to get some experiments and some insights and the fundamentals on this type of experiment. So here we have it under construction for the future. Here is our first experiment about reaction. Here is the surface area of an alumina catalyst. We are gonna use a catalyst made of alumina. We are gonna place the catalyst inside of this cell. We are gonna use actually liquid nitrogen that we are keeping in this flask here to keep the conditions of the right conditions for the experiment, based on the different pressures that we are obtaining with this digital meter here and this pressure sensor here. We will be here is the catalyst, by the way, you can have a look at it. So the liquid nitrogen will go here, and based on the different pressures and the different absorption inside the pores of the material, we will be able to determine what is the surface area of this material, which again is very important for the design of any catalyst. When you have a catalyst, what you want to do is maximize the surface area so that with the least of the material, all the area is exposed and the reaction is more efficient. Here we have the packet bed catalytic reactor, and you can see here, I think there is some different flows with different reagents. Here, some water, some propylene as well, and this experiment, this is under revamping. Actually, so this year we are not running it. Catalytic hydrogen production. This is one of our newest experiments, as you can see from the fancy setup, designed by one of our PhD students, Simona Mazzone, and her PhD advisor, Francisco Garcia. And in these experiments, the students, they have different powders. They are able to design their own catalyst. They can decide what is the percentage of the different materials that they want to mix, because it takes a little bit long time for the catalyst to get homogeneous. The students that come the week after are the ones that they will be testing the catalyst that has been previously done. But I think it's a kind of nice interaction, and they will be able to see how the different components like ruthenium, cesium, silica affect the performance of this catalytic reaction against hydrogen. And the last of the experiments that is active for now is the CSTR continuous stir tank reactor. And for the residence time distribution. So in this experiment we are not doing any reaction, but we just based on the different flows, we are able to determine what are the different mixing times that we are having inside of the reactor. Continuous operation is very important and is more efficient than just using a reaction in batch, as you will always need to stop and start again. So this is what we are teaching the students here, how the air or the different material goes inside the reactor, how it mixes for different nitrogen flows, for different flows of the mixture, and more importantly, what we are working here is also when we are using a baffle inside of the stir tank reactor. We are not using a baffle, or when we are having the different mixing flows. And you might have seen other experiments also around, but those are not, those do not belong to the Chemical Engineering Lab 3. We have some experiments related to process separation 2, led by Dr. Enzo Mangano. I think there are other experiments also around here that are from different academic years. So I do hope you have enjoyed the video. I hope you have learned a little bit what are the type of experiments that we are doing here, how you get from studying first, second year the different theory, the different fundamentals, and how you come into the lab and you are able to practice those fundamentals by experimental practice. Very useful for your future in industry.